For this, we have write an electron configuration for each ion. Okay. So luckily for us, electron configurations for ions aren't too bad relatively. So electron configuration for ions. The ones you have to really focus on are the ones that are typically just break the typical off-bulb principle for electron configuration. Those ones are typically found in transition metals because sometimes you have to do some rearranging to make sure you have the right thing. So now, let's go ahead and start with oxygen 2-. So we're going to refer to our periodic table here, okay? So as you count through, oxygen is indeed the 8th element. So we want to make sure that we have all the superscripts should add up to 8 theoretically. So I'm going to start just writing it out. So we have 1s2, 2s2, and the reason why I can put that is because hydrogen and helium have been passed, so has lithium and beryllium. And now from boron to oxygen, that would be 2p4. But we're not done quite yet. They say oxygen 2-, so this is not just your regular oxygen. Instead of it being now just 8 in total, we're adding 2 more electrons. So we're actually going to fill the p orbital, and it's going to be instead 2p6. So oxygen 2- is actually what it would strive for in order to end up like neon. This is it trying to complete the octet rule. It's now accepted 2 electrons, filling up its valence shell, and now it's completely satisfied, which is why it resembles neon. Okay, so that would be for oxygen 2-. For Br-, okay, similar thinking here, where it wants to now fail the octet rule and become like a noble gas, but bromine is all the way down here, element number 35. So we're actually going to go through now. So we have 1s2, 2s2, 2p6, 3s2, 3p6, and then we're on the 4th row now. So that's 4s2. We do pass transition metals, so that'll be 3d10, and now we're back out, and it will be 4p5 currently for bromine. And all these do theoretically, well, should add up to 35. We can actually just double check that just so that we don't have to check for the other ones. So we have 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 5. 35. Perfect. But this is Br-. So like the oxygen now, we're actually going to fill that p orbital because that is what happens when you add 1 extra electron. So now the bromine minus resembles a krypton atom. Okay? So now Sr2+. So this is strontium. Okay? So if we go over to the periodic table, Sr is right here on the 5th column. So now even further than bromine, so we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and then we have 5s2. So this right here, strontium 38, directly, this is what it would add up to, which makes sense because 4p6, we knew that 4p5 was 35, and then 36, and then if we add 5s2, that'd be 2 more, so 38. But we say strontium 2+. So for this, it's actually losing 2 electrons. So it'll lose it in its most outer shell to become kind of like bromine. It's going to become like krypton, because these 2, the most outer electrons, that's the valence shell, are actually not going to be gone. It lost the 5s2. So this will be an electron configuration for strontium 2+. So now we're dealing with cobalt 3+, okay? So if we refer to it, so cobalt's right here, okay? So it's going to lose 3 electrons. But let's first draw out what it would be. You would have now 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now where it is 3d6. Hopefully I counted that correctly. 1, 2, 3, 4, 5, 6, 7. So 3d7. Sorry about that. Okay. So now this is going to be a quite interesting one. Okay. Because you would assume that if cobalt lost 3 electrons, we just go based on the order. We would kind of want to lose it from the d orbital, because the d orbital and the s orbital are relatively close to where it could lose from it and it would count technically as its outer shell. But let's just say we just lost everything from the d orbital because the one we wrote last. So -3, we would now have 3d4. Okay. But here's the thing though, okay? When it comes to transition metals, this is where it gets tricky. The orbitals start to get a little bit wonky, okay? 3d4, that is so close to 3d5 to where all the orbitals are half filled, to where it would actually prefer that. And so that means it would actually take an electron from its outer shell, so the 4s, and this would become 4s1, 3d5, because now we have 2 shells that are halfway filled, okay? This theoretically would be the most stable cobalt it could get, and what it looks like, it would be resembling, if we did -3, so 1, 2, 3, this would be kind of like what chromium would do. So that's what cobalt's doing. Cobalt is mimicking chromium, because actually this is what chromium would realistically do if it's around its electron configuration. So now for the last one, copper, and I hope you're seeing in regards to how transition metals do get a little bit weird. Copper, okay, is all the way over here. All right, so it has 1s, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Okay, it's 1 away from filling its shell. So with that being said, for this one, we want to make sure that we can approach it the best way. Copper doesn't really lose much from going from 3d9 to 3d7, because why would we then get rid of the outer shell? But the tricky part is here is that the original copper ion would not even be 4s2 3d9, it'd be 4s1 3d10 as a full shell. So now here's where it becomes more complicated. If I put it like this, why would I first get rid of the 3d when I can get rid of the 4s? Because there's only one of them. I don't want to keep going back and forth. So with that being said, we actually would just get rid of this one. And now we would actually just have 3d10 as you got rid of 1, and then it would be 3d9, okay, when you got rid of the second one. So with that being said though, after reviewing that, we'd actually have to go back to the cobalt, because cobalt, just to make sure that we did it correctly, typically in its natural state would be 4s2 3d7, and so if we got rid of the 3 plus, it would go down to 3d4, and then we rearrange. So for this one, I'm going to be honest, I'm not too sure about. And same thing for this copper, just because transition metals do typically go through very different changes, and they definitely break through the off-ball principle based on how the shells are in terms of their energy levels and everything. So let's go over to here, see what our colleague did. Oxygen 2-, so then they added 2 more and it becomes like neon, so 1s2 2s2 2p6, perfect. Bromine, same thing, now 4p6 is the end. Strontium gets rid of the 5s2, 4p6 is also the end. Cobalt, on the other hand, yep, 4s2 3d7. Let's see what we get. We get 3p6 3d6. So what they did here was they just got rid of the outer shell completely. It does make sense as well. I was just thinking more so that that's just quite unstable, because I mean, if it could fill this outer shell, it would, but I guess ions do work a little bit differently. So with that, I do apologize. Let's just go over this again. We don't have any more of this. I'm going to leave that here as reference. I'm going to have just 3d6. So it seems that what they're doing here is that when you do get a ion, a cation, as losing electrons, specifically for the transition metals, you want to start from the outside as much as you can, just go in. So yes, the S's, the S shell orbitals, we're gotten rid of first. That's how we end up with 3d6. So for copper, before we just go see the answer, let's see if we can apply it here. So for this one, as we said, we start out with 4s2, 3d9, right? So if we want to do 2 plus, it'd just be minus the 4s2, leaving us with the 3d9, okay? Even if we change it to where it was 4s1, 3d10, which is what copper would actually be as its natural state, we just got rid of 1 here, and then we got rid of 1 here. So we should theoretically get 3p6, 3d9 for copper. Let's cross our fingers and hope. Okay, 3p6, 3d9. So with that being said, though, this is correct. And the lesson here is that you want to start from your outermost shell and just keep subtracting in, and do not try to rebalance it to make it quote unquote more stable. Just keep subtracting from your outer shell as is, okay? And with that, let's move on to the next question. But first, let's take a quick water break.